The law of averages is one of the most intuitive mathematical facts about reality. When we flip a coin repeatedly, or many coins at once, we expect heads and tails to show up in roughly equal amounts. Otherwise, it wouldn't be a very good coin, not a fair one at least. Yet, what feels so intuitive is quite tricky to put into precise mathematical statement. Such a theorem exists. It is called the law of large numbers. The goal of this video is to understand what exactly this law is saying, why it needs to be formulated so carefully, and how it makes coin flips predictable, despite all their randomness. One of the problems lies within the word roughly. The coin cannot keep perfect balance between both sides. A little imbalance is to be expected. But how much? After all, streaks are not impossible, they can and will happen. Also, how many flips are needed for the law of large numbers to manifest? 100? Are we guaranteed after 100 flips to not be too far away from a 50-50 distribution? After all, throwing 100 heads in a row is technically not impossible, so we definitely have no mathematical guarantee. What is this law really saying, and how much can we rely on it? These are the questions I want to explore with you in this video. Let's start small, with a single coin. I can flip it by tapping it, or let it flip itself on repeat. We can compute the proportion of flips when it has come out tails, say, by collecting the outcomes in a list of numbers, where 0 stands for heads and 1 for tails. The number of ones in this list, as a proportion of the total number of flips, is simply its sum total divided by its length, or in other words, its average. We can compute it like so. Now, as I let the coin flip repeatedly, its average indeed approaches 0.5 in the long run. Even if I start the process over, the share of tails will, given it enough time, get closer and closer to 1/2. We can visualize this process by plotting the partial averages in a coordinate system. For that, let me first collect them in their own list. Now I create a plotter and give it that list of averages as its y-coordinates. Let's run the whole thing. And yeah, after some initial fluctuations, the graph flattens out at 0.5. Let's speed things up a bit. Again and again, in every new run of coin flips, randomness is followed by consistency, as if the coin could keep the score even and had the memory to do so. This balance of heads and tails can be disturbed significantly. It is not impossible to start with, for example, 20 flips that just happen to come out tails. I can make this happen here on purpose by swiping on the coin instead of tapping. And then I let the coin flip at random again. Still, the average will, in time, approach 1/2. Mind you, not by throwing in a few extra tails to balance out the streak of heads, but as both outcomes appear in still roughly equal amounts, the effect of the streak gets diluted more and more so that as to eventually become insignificant. This phenomenon is called regression to the mean. I can even start off the coin with 100 tails in a row, and even then, given enough time, the average will approach 0.5 nevertheless. Now, of course, regression to the mean is not a real explanation of the law of large numbers, because if you think about it for a second, it would be a circular argument. but it is a piece in the puzzle of understanding how predictability comes out of randomness. In this graph, a typical run of the experiment ends up within a small range around 0.5. Let's fix the number of flips for a second. Some runs will land outside this range though. Those are the outliers. Out of all possible runs of a certain length, say 1,000, we expect the large majority to end up inside, not too far off 1/2. But a number of tails that is significantly above or below 500 will be extremely unlikely. So the question now becomes, if for a given number of flips n the possible number of tails is not evenly spread from 0 to n, what does its actual distribution look like? We will investigate this in the next section. In order to find this distribution, let's fix the number of coin flips to, say, 20. Here's a whole row of coins that we can flip at once. Collecting the number of tails in a list, we see that most entries are indeed in the vicinity of half the number of coins, peppered with some outliers. We can turn this data into a histogram. By default, the x-axis only goes up to 10, but let's adjust it to the number of coins that we actually have. We get this nice bell shape. Now before I go deeper into this exact shape, let's also keep track of the number of flips that have occurred. Like so. Most tail counts lie between 5 and 15. Tail counts above or below that range are comparatively unlikely. They can still happen, and will, given enough trials. Even a streak of 20 tails, or no tails at all, is not strictly forbidden, just very unlikely. If we ran the simulation long enough, say 1,000,000 times, such extremely unlikely events are ultimately bound to happen. Thinking back to a single coin, we can say that any such coin will, after 20 flips, most likely already be on its way to a balanced average of 0.5. Or in other words, out of all the 2 to the 20 possible runs of this experiment, the vast majority of outcomes will have between 5 and 15 tails. Only a small fraction will contain fewer or more than that. If you have ever seen a Galton board, this is exactly what it is demonstrating. Each ball's path is a random succession of left and right turns. Most such paths will not drift too far in either direction, only a small fraction will. Overall, the balls form this nice bell shape. I won't go into the exact mathematical formula for the probability of each number of tails. Rather, I want to explore how this shape changes over time as we increase the number of coin flips. The long-term evolution of this distribution lies at the core of what the law of large numbers states. Let's get serious about the number of coins. I can create a whole stack of 100 or more, like so. The majority of outcomes land between 40 and 60 tails, which is wider but also narrower than the 5 to 15 span from before. The absolute spread of the distribution is larger, but relatively speaking, as a fraction of the overall horizontal span, it is only about half as wide. Let's go to 1,000 coins. Well, we don't see much because the bars are now so thin. But I can increase the size of the histogram spins to 10, for example. the bell has gotten even thinner. Most runs of 1,000 coins come out tails between 450 and 550 times, a mere plus or minus 5% deviation from the center. This is regression to the mean in action. There appears to be a magical pull towards it, even though we know there can't be one. Let's also not forget that in absolute numbers, the bell shape still becomes ever wider. All of these visuals are not an explanation of why this is happening, and I won't try to give you one in this video. But by playing around with this, especially by increasing the number of coins, we can get closer to a mathematical formulation of what it means for this distribution to become narrower and narrower. In this sketch, I use n to designate the number of coins that we flip. And let's also call x this random variable of the number of coins that come out tails, which is any number from 0 to n. Then these sketches describe the probability with which the relative number of tails, x over n, takes on any specified value between 0 and 100%. The key idea now is to fix ourselves a level of deviation from 50% that we are willing to tolerate, meaning any outcome that is not farther off than that percentage, say 5%, we would still consider typical and not an outlier. Then we would expect that we just have to wait long enough, that is, increase the number of coins n, until almost all of the outcomes give a number of tails x that lies within the chosen margin. And by almost all, I mean that the fraction of typical outcomes, the area under the bell curve within those bounds, gets closer and closer to the total area 1. And there's nothing special about 5%. We could choose a narrow margin and still observe the same thing. We would just have to wait a little bit longer. And if we want to get closer than 0.001%, sure, just make n large enough. So the law of large numbers is a statement about the limit behavior of probabilities, as the number of identical repetitions of an experiment grows larger and larger. Before I present to you a fully mathematized version of this theorem, I want to go back to the data and connect it to these inequalities. Really pin down where in there the limit value of 1 lies. Back in the simulation, the number of tails is collected in this list of numbers, so these are the values of our random variable x. Let's also keep track of the length of this list, so the number of trials. And I also want to give the number of coins its own persistent input box. Now let's count the number of entries in that list for which the relative proportion of tails, that is x over n, is above a certain given number between 0 and 1. In other words, x is larger than the product of that parameter with the number of coins, which I can compute like this. Now I create a comparison list with its two arguments being the list of data and that cutoff number of tails. We see that whenever that parameter value is largely below 0.5, almost all entries in that list fulfill the inequality, and if we are well above 1/2, then almost none of the number of tails is above that cutoff. Finally, we can ask what relative proportion of the number of trials gives us a number of tails above that cutoff. In other words, what is the probability that x over n is larger than 0.771 in this case? And this is simply computed by taking the average of this list of zeros and ones. Here it is. This probability also varies from 0 to 1, just in the opposite way. And most of its variation actually happens whenever the cutoff value is chosen close to 1/2. Let's set it at 45%, and we see that only about 20% of all trials lie below that. But that is still too much for my taste. We can increase the number of coins, and now the distribution should narrow, so more of those trials should lie above that cutoff of 45%. I also increased the bin size as before, just so that the graph becomes more visible. And now we see that, around 99% of all trials give us a number of coins greater than 45%. If I set the lower cutoff closer to 1/2, fewer trials make the cut, but we can compensate that again by increasing the number of coins. After all this exploration, we are now finally ready to precisely state the law of large numbers in its weak form. There's also a strong version which I will not go into here. Let's just settle notation and vocabulary here. N is the number of flips. An outcome of n coin flips is just a sequence of zeros and ones of length n. And the random variable x here denotes the number of tails in any particular outcome. Then we can say that for any cut of t less than 1/2, however close to 1/2 we choose it, the probability that the relative number of tails is above that cutoff tends to 1 as the number of flips tends to infinity. Here's the visual again, here's the cutoff t, and the nice bell curves become narrower and narrower around 1/2. So eventually the part of the area under the curve right to the right of t becomes larger and larger, and the part to the left of it tends to 0. An analogous statement can be made for t larger than 1/2, or there's also the symmetric version. For any positive bound epsilon, however small, the probability that the relative number of tails lies within epsilon of 1/2 tends to 1 as n tends to infinity. In the next video, I want to delve deeper into the reasons why the law of large numbers holds. In particular, a very cool visualization showing how this bell shape actually comes about and why regression to the mean is actually happening. In the meantime, follow the link in the description to get an interactive version of everything that I've shown you in this video. There you can explore the coin flips on your own. And as a particular challenge, see what happens if you actually change the probability of tails. So if you make the coins loaded. What statement and prediction does the law of large numbers make in this case?